Bonjour, merci de participer à cette troisième journée de DataXDays et à ce deuxième talk de la journée. Je vous rappelle que DataXDays a lieu tous les mardis du mois de juin. Ce midi, on nous a parlé sur Machine Learning et imagerie médicale. Maintenant, on continue avec PySpark et Data Architecture. Le prochain talk sera en anglais, so I'm switching to English right now. Next speaker is a big data engineer, consultant, and contributor for Spark. He is going to talk about the internals of speeding up PySpark with Arrow. You can ask your questions in the comments section, and the speaker will answer at the end. Let's welcome Ruben Berenguel. Ruben, the public is yours.
In French, but my French is not good enough. So the talk is going to be about PySpark, which is how we call the Python API on top of Spark. And I will explain why you can use it, and don't worry about the speed, because the changes in Spark 2.3 and 2.4 have made it super fast. So I will explain and convince you that it's good to use and ready for prime time. So I'm a big data engineer. Well, I was a mathematician, now I'm a big data engineer, and I work at Hybrid Theory, which is a digital services partner and powers smarter and data-driven advertising for brands and agencies. We use big data and machine learning. And the structure of the talk is as follows. So we will start with a bit of what is Pandas, which if you use Python, maybe you know what it is, but maybe you don't know some of the internal details that are important for why and how we can speed it up. Then what is the Apache Arrow project, which is used internally by Spark to speed up Pandas. How Spark works, which maybe you don't know, and I think it's always interesting, especially because you need to know how Spark works to understand how PySpark is able to interact from the Python side to the Scala side, which is the core of Spark. Then I will talk a bit about plans optimization, so the magic that Spark does behind the scenes to make sure everything is super fast. And then how you can use UDFs, that's user-defined functions, in PySpark and use Pandas in them. And if we have time, I will show some examples about how you can use these possibilities to make them faster. So let's start. What is Pandas? It's a Python data analytics library. It's used everywhere. So if it's a job offer that says Python data, Pandas is there, that's for sure. It's efficient. So it's columnar and has a C and Python backend. So the backend is super fast because Python is not the fastest language, but it has something called Python, which is a kind of it looks like Python, but it's almost like C. And the backend of Pandas is written between this and C. And it's columnar. And maybe you think, you've heard that term before. What is a columnar database or a columnar? What's the magic that makes columnar being faster? The thing is that imagine that you have a table with a lot of columns, like thousands, which can happen in big data analytics projects. And you want to sum one of the columns. Maybe that's the cost of something like the phone bill or the energy consumption of a house, which will have a lot of rows. If you do that row by row in a CPU, well, you need to load everything into the cache, and then when it's in the cache, you can sum it, or you can get into the CPU somehow. If you start row by row, you start with one row, move it to the cache, go to the next row, move it to the cache. You need to keep loading rows. But if the data is stored by column, you can load the whole column, like everything in one go. This may sound like a small difference, but when you are working with a million rows, a billion rows, this difference adds up. And that's why columnar databases, for instance, Redshift, the Amazon's Postgres derivative is columnar, Pandas works columnar, there are several. This is why they have a big impact in performance terms. Pandas has a special way of managing the columnar data. In particular, this is a Pandas data frame, which is the way that Pandas table is structured when you create one, like you have a column with floats, a column with strings or objects, I mean the A, B, C, D in the column B, a column with integers, and a column with floats. The way Pandas handles this is that it tries to keep like with like. So you will try to have floats together. How this is done is that Well, the indexes are kept aside because indexes are special and usually it's a small amount of data. But you will try to store in memory the floats with floats in the same memory area. Same with the strings. Strings and binary objects or anything that is serialized goes together, and the other one will be for integers. This is stored in something called a block manager, which handles blocks. So each of these blocks, it's a block, and it's handled by a block manager. And these are structures that are kept in memory as a block. This is where Arrow enters the scene, because the concept of the in-memory blocks ties together with the Arrow memory storage. Arrow is it's a cross-language in-memory columnar format library, which is a kind of a mouthful, but basically it means that it offers a unified API, so different libraries and different languages can use in-memory storage in the same way. So you don't need to learn a new way of doing it in C or in Python or in Scala or in Java, Rust. You can use Arrow, which is a library that has APIs for different languages. It's optimized to be efficient in all of these languages. So the whole point of the library is that it's fast. Otherwise, we lose a bit the point. And it integrates seamlessly with Pandas. I mean, it was created by the creator of Pandas, Wes McKinney. So he knew how Pandas work. He had an idea, and that idea turned into Arrow, and they were able to talk among each other. Some projects that use Arrow internally are Pandas, for instance. I mean, that's for sure. Spark for the optimizations that we talk about. Parquet, the file format, which is a columnar file format. Dask, which is a distributed computation system written in Python. Ray, which is another one, and several others. And they keep appearing because Arrow is getting a lot of traction at the moment as a library that you can use. So Arrow offers a different way of storing the data in memory in a columnar way. How does it? So we have a table, I mean, as before, and it's stored in a concept called a record batch. This is like it could be like a set of rows. It's not exactly a set of rows, but you can imagine that it's like a block is sent, and then another block, and then another block. This makes it streamable. So anything that goes into Arrow can be sent in blocks of record batches or in batches, and you can do a kind of micro streaming or what's it called? Well, I don't remember the name of quick streaming. So we have this record batch, which is a set of rows. It comes with some metadata, so it can be streamed in isolation. So you don't need to know anything about the previous batches, so you can plug into the stream on the fly. And the data is stored also by columns in blocks. So if you squint a bit, this looks a bit like the image before we had with the colors in Pandas. In the end, an Arrow table is a set of blocks, and these blocks, which are record batches, look like the blocks in the block manager. And that's kind of the magic that makes Pandas being able to talk the Arrow format and Arrow be able to talk the Pandas format. So Arrow uses record batches, Pandas uses blocks in a block manager, and basically you can pass from Arrow to Pandas data frames just by converting them. So if you move away from the screen, okay, you see like blocks of color that look similar. That's the whole point. You can pass from blocks in the block manager as a whole record batch, and you can pass from a set of record batches into a block manager. Now we get to Spark, which is the favorite big data framework nowadays, I think. At least that's what I hope, because I work with Spark and I've been working with it for 4 years already, or 5. Lost track. It's a distributed computation framework, which is open source, which I think for me, it's the most important part, because you can go there, check the code, understand how it works, investigate, improve, help. Help is always welcome. And it's kind of fun to help, because you will learn things that you couldn't otherwise. It's quite easy to use. The API of Spark, I think it's pretty neat. It's a bit rough in places, especially in the new areas that are under development, but it has been available for I think, close to 8 or 9 years. So it's pretty much stable. There's a lot of documentation. One interesting feature is that it scales horizontally and vertically. So usually you can go with a larger machine, and eventually, if a larger machine is an issue, you can go to having more machines. Having more machines sounds better because, that's the whole point of a Spark. You have like a billion machines and everything is going to be faster. But you need all these machines to communicate and send data from one to the other. And the network is way, way slower than having everything in one machine. So I would recommend that if you can, usually a large machine is as expensive as the equivalent number of the small machines. And in terms of time, one large machine will be better. So think about that as an optimization for your own work. So how does a Spark work? First, you need a cluster manager. This is whatever is able to manage a set of machines. This can be Yarn, which is yet another resource negotiator. I mean, this is the oldest one that is available, and it's kind of the most widely used, I mean, to be fair, for Spark. Mesos, which it's pretty good, but it doesn't seem to have as much traction lately. And if you're in the bleeding edge, you have Kubernetes, which it's used to handling other kinds of clusters, which are not Spark, which is kind of the fancy thing. So you can have a Kubernetes cluster with all your services, and you can have a Spark running beside them, which is kind of cool because it means that you can have a very good optimization of your resources. You also need some kind of distributed storage. Usually it's the Hadoop file system, HDFS, or something equivalent like the Amazon Web Services S3, or the blob storage from Azure, or I don't remember the one from Google, but all of them offer a Hadoop file system-like API, so you can use them as distributed storage. So when you write code in your Spark program, it is going to run in the driver, which is the kind of the main machine in the system. The driver is the one that is requesting the resources from the cluster manager, and these resources are needed to run tasks. So you have a cluster manager that owns a set of machines. You want to run some tasks, and the driver is going to request, hey, give me some machines so I can run these tasks that the human we have here wants to compute. Inside these machines, some executors will appear. I mean, executors are where the computations take place. You usually don't need to worry about this because the cluster manager handles that and the driver handles the cluster manager for you. But I mean, executors is where the magic happens, and when there are errors, usually they are in the executors. Each executor has a local cache, so that's in the small machine that it's in the middle of nowhere in your cluster of a million machines. It's going to have its own cache, it's going to compute each task, it's going to have its own memory. Now, how can we make sure everything is safe? I mean, the main issue with big data computation is that if you are running in a 1,000 or 100,000 machine farm, well, some of the machines are going to fail. And when you have a lot of machines, failures happen constantly. This is what happened with MapReduce and why Google needed to do something with its own big data structure, that you needed a way of making sure that you could recompute whatever needs to be recomputed. The special thing that makes Spark special is that it has a data structure that helps you with the recomputation. So the original paper that gave rise to Spark, or more exactly, I mean, the original idea that made rise to Spark, and then they wrote a paper about it, it was about the resilient distributed data set, the RDD. And the paper is called the RDD paper. And I think I added a link at the end. So RDD is what allows you to, okay, I had 10 machines die. How can I recompute everything that has been lost? I mean, I don't want to recompute everything, because if I recompute everything, I lose a lot of time. Maybe only one machine died. Maybe one machine failed and I have 1,000. It would be a waste of recomputing everything. That's done thanks to the RDDs. RDDs are defined in the Scala code, and they are case classes in Scala. So we have an RDD. This is my representation of a case class, like a happy case class. And to be an RDD, you need to have 5 methods, 2 of them optional. You need to have partitions. So that's where the data is and how the data is partitioned across machines. So you have a data set that is like, I don't know, imagine the people that live in Paris. You can partition by postcode. So you can have, well, I don't know how many regions there are in Paris, but probably there are, let's say 50. You could have 50 partitions. If you have 10 machines, each machine gets 5 partitions. So it would be easy. But you need to know how this is done, and that's what the partitions give you. The other one is a set of preferred locations. This is optional. So if you know that one machine already has the data for one of these partitions, maybe you have computed something before, or maybe the local disk for one of these machines already has this data. If you know this, Spark is smart enough that it can say, okay, this machine is going to compute for this partition. Don't need to move that data away. But it is optional because usually it doesn't happen. For me, the kind of interesting one is compute. Each RDD is doing something. So you take partitions and you get output partitions that are computed from the first. This can be sum, this can be a filter, but you get data in and you get data out. And this is achieved by compute. So you go from a set of partitions on top to a set of derived partitions. Let's say that you are multiplying by 10% everything in the cost column of some data. So you go from having a cost on top to 10% on the bottom. Now, one of the Ds in the RDD concept is that you can recompute. It's the resiliency. This is achieved by the dependencies. So an RDD knows where it comes from. So it knows that the parents of this RDD eventually come from loading data from somewhere or doing some operations. And then it knows that, okay, when I have loaded the data, I have computed my 10%, and I have something. So if one machine dies, the driver and the RDDs themselves know that, okay, if this machine has died and then it lost partition 100, we can go back and know, okay, partition 100 comes from loading the data from partition 25 of the input data, computing this, this, and this. So if you lose one machine, you can recompute only that. This is achieved by the dependency set, which is also called the lineage, like the ancestry of the RDD. And finally, and this is optional, it's a partitioner. So it's a way of defining the partitions according to some key. So if you have the postcode, you can say, okay, use the postcode as the partitioner. If you have social security numbers, you can use that. Or Spark usually is smart enough to do something sensible if you just don't define it. So it's usually not needed. And all this was for the Scala side of the story. Then we have PySpark. So when Spark started, it was a pure Scala project, but eventually, a lot of people use Python, especially in the data science world. So I don't remember who it was, but it was decided that having a Python API on top of the Spark core would be helpful. And to be fair, I think PySpark is achieving a lot of use lately. Every time I give a talk about Spark, I ask how many people are using PySpark, and the number keeps increasing, which is, I think it's cool. I like Scala. I also like Python. So I like seeing that usage is growing in both sides. So PySpark offers a Python API on top of Spark. If I say, I will be saying PySpark for the Python API on top of Spark, and either Spark or Scala Spark to differentiate with the Scala version. How does PySpark communicate with Spark? Because Spark is written in Scala. They are pretty different languages, at least until Scala 3 appears. And that's for another story. It's using something called Py4G, which is Python for Java, or it should be Java for Python, but I don't know. I didn't give the name for this. This is basically an API that allows you to start a JVM, a Java Virtual Machine, from Python. So when the Python driver starts, it's able to start a Java virtual machine that starts a Scala Spark driver. This is achieved in a really, really small amount of code. And I added it into this slide because it's like I was blown away because this says, okay, get me a Java virtual machine, load everything we need from Spark, and give it back to Python. This is Python. And with this, you are able to communicate with the core of Spark. So now we are in Python land, and this is a happy RTD class in Python. This class has a property called self._jRTD. Underscore because it's supposed to be private, but nothing is private in Python. And the J from the JRTD is because every object we create in the PySpark API will have an equivalent one in the Java API or in the Scala API. So when you create an RTD in Python, this has a mirror image in the Scala API. So when you load something like, okay, I want to load from HDFS, all the people from Paris. Python communicates with Scala Spark via the Py4j protocols. It creates a Scala RDD, which contains this data. And this self_jRDD has a reference to that one. So nothing is really in the Python virtual machine. Everything stays in the Java virtual machine. And if you inspect the PySpark code, you will see a lot of _j properties. And well, I mean, you should remember that if M is for murder, J is for Java. And I mean, I'm not a huge fan of Java, but I like Scala, so I think it shows. This communication is done through Py4j. So Py4j has a huge API that allows you to pass information from one to the other. So the structure in the Python area of the code base of Spark, it's complicated, but it's not super complicated. I mean, there are kind of two entry points. One is the RDD. I mean, this class has the same name that the one in Scala. And then there's one called pipeline RDD, which is a subclass of RDD. This one is the one that has the methods to be able to compute. Because if you think about it, if you are computing something, you define the computation in Python in general. So, I mean, I don't know, you want to multiply by 2, but you write that as a lambda function in Python, or you write some Pandas method or something, but it's going to be Python. It's never a Scala. And the compute method we had in the RDDs in the Scala side are Scala. Pipeline RDD, it's the glue that moves the data from one side to the other. So pipeline RDD, it's creating in the JVM a Python RDD, which is a subclass of the Scala RDD. And I have drawings in the next slide because it gets confusing at this point. So here we have an RDD. It's a JRDD, so it's in Python side. We want to map it with an F. This F is a Python method, whatever. Multiply by 2, for instance, a lambda. We have a pipeline RDD, which is still Python. We store this F, like multiply by 2, in a field called func for function. We point the previous, so like the lineage of this pipeline RDD, to the RDD in Python. And we need to add a JRDD to this pipeline RDD because it's a subclass, so everything needs to match and we can't lose track of who is the parent. Okay, this JRDD, it's a Python RDD in Scala. And the interesting thing here is that when you look into the dependencies of this Python RDD in the Scala side, it's going to point back via the previous pointer to the JRDD we had in the RDD, which is back to a Scala object. So we have a way of going from, we're kind of making a weird turnaround from Scala code or JVM code through Python, again to JVM code. And now we have the compute, which is where something happens. And this is where we have the func. But we still don't know how to compute something that is defined in Python in Scala. I mean, Scala doesn't know Python. So how can we do this? This is where we have the magic, as I call it, because really something kind of smart is happening there. So compute is going to run on each executor. I showed that in one of the first slides where I had the small executors. Each executor is going to start a Python worker. So that's like a separate process that's going to compute something that Spark Scala is going to be sending data to this worker. This is done by a Python runner, which is some class that starts the process. And that's beyond the interest. We have a Python RDD in Scala. Python runner is going to be passed the func because this is the function we can execute. Information about the parent, and again a compute because this extends something else, so we need to keep sending things. But this starts a Python process. Like if you were going to a console and writing Python, basically Python runner is doing that with a lot of imports and a lot of pipes and a lot of sockets, but it's basically doing that. Then Python runner is going to say to this worker, okay, I'm going to send you all this data. It starts with the function as a pickled object, and then the data is flowing from one side to the other. The worker is computing using this function the data that it's streaming, and when it's done, everything is finished, and Scala knows that computation has been finished in Python. So, I mean, if you think about it in a kind of a conveyor belt or a streaming process, workers are standalone processors of streams of data. So you can imagine that the worker starts, gets a function like multiply by 2, and it starts getting numbers. And when all the numbers are over, the data is being passed to the JVM. The worker has finished, it can be closed. It's connected by a socket to the JVM that has started it. It will load any Python library that is needed. So if you needed some machine learning, it could be started. It deserializes the function, I think I mentioned that before, and all the data that comes from the stream. Applies the function and sends the output back. Basically that. I mean, it's not super complicated, but it eventually gets a lot of moving parts. And all this story looks super interesting, I think. I mean, I like it, but there's something about the Spark that I have been not mentioning, that Spark is pretty smart and it's able to optimize what you compute. I didn't say anything about optimizations. And it's because RDDs are not optimized. So when you define RDDs, basically you define a graph of computations and that's it. If you want to have a code that it's nicely optimized by Spark, you need to define data frames. Data frames are just an abstraction on top of RDDs. So deep down of the Spark code base, everything is RDDs. But you have data frames and data sets, which are kind of the type version. So when you have a definition of a computation defined with data frames, Spark generates a plan. So I mean, you can think of it as a database. When you use any database like MySQL, Postgres, Redshift, BigQuery, you define, I don't know, select everything from this table and join with this other table and group and count. The database is going to say, okay, I mean, this table you are joining, I need to read the data from this specific location in this specific disk, and I can compute these in such a way. Basically, Spark is optimizing in the same way to compute. And this is done, there are several ways that this optimization is happening. One is the cost-based optimizer, which is similar to how a database works. The other is the catalyst optimizer, which basically it tries to push down as much as it can and remove as many branches of the computation as possible by kind of merging things together or doing fast optimizations. The thing is that if you define data frames with Python operations, you need to execute them somehow. And depending on the function, the optimizer is going to choose either Python UDF runner, that's a user-defined function runner, or the Python arrow runner, which is kind of, you mentioned run arrow at the beginning. Both extend Python runner, which is the basic one for RDDs. And both are pretty much similar. So you have UDF runner and you have a worker because that's the base of the computation for Python. You serialize data. Data is deserialized. You apply, this was too fast. You apply the F and you send the data back. Easy. And for arrow, it's similar, but it's not exactly the same thing because you serialize data in the arrow format, which is done in the Java side like pretty quick. And when it makes it into the worker, you convert it to Pandas. Arrow and Pandas formats are pretty much equivalent. So this is like doing nothing. deserializing in the worker for the UDF runner is expensive because it involves pickling and pickling. But to Pandas, it's pretty much instantaneous. Applies F to the column. If you can define your method as a columnar operation, that is super fast in Pandas because Pandas is columnar. And it sends the data back as arrow, which is also super fast because Pandas and arrow are more or less the same. So you have saved a lot of the serialization cost. How much is a lot? So if you check the original blog posts about from Databricks about how this speed up could be, it's between 3 and 100, which sounds like a lot. And to be fair, I had to check because if I don't see it, I don't believe it. And also I wanted to show some examples about how this looks like and how you can use it. They will be pretty quick. I mean, the basic one, it's using two pandas, which is basically, I mean, I defined a data frame with identifiers and a column which has a random number without an arrow. So I set this flag to not use it to see how slow it can be. And then I convert the data frame to pandas like that. You can do that regardless of whether you have arrow enabled or not. And the other one, as you can see, the only difference is that the true or false. I had run this several times for both sides. This is what happens when you run it without the arrow optimization. So as you keep increasing this number here, the 2 to the 20 power in the range. So you start with 17, 18, 19, 20, up to 22. It keeps increasing as you keep increasing. 23, you couldn't do because I ran out of memory on my machine. Because the process in PySpark was using too much memory. What happens when we use arrow? The difference is pretty significant because, I mean, you can go farther. You can go up to 20. I think I could go up to 26, but it didn't make much sense to add it to the table. The speed up was like between 10 and 17, I think. The table is at the end of the slides. But this is like, I mean, the difference between the optimized version and the unoptimized version, it's setting a setting to true. So what's easier than this? And another one, it's using group by. I think group by is one of the most common things you're going to do in the big data, data engineering, data analytics, data science operations. I mean, eventually you're going to group by customer and sum the cost. You're going to group by item and compute something. I don't know. In my day-to-day job, I'm doing group bys all the time. So what you can do with group bys by using arrow and pandas. First, as you can see, this range here, it's like the one before, but I'm adding also a spent column. And I'm defining a UDF. This is the pre 3.0 format for UDFs. This has changed in, well, it hasn't changed in 3.0. I mean, this is still valid 3.0 code, but the Spark 3 will have a way nicer way of defining this. So this is just computing basically the deviation from the mean from the expenses for a data frame. This is a computation that you may do for fraud detection, for instance. So if the expense is too away from the mean for this user, maybe it's a fraudulent expense. And you do this by grouping by ID and applying this UDF. And oops. This is how you would do that in exactly the same in Spark 3.0. So if you, I don't know why there's an empty slide there, but if you see there's a decorator here, Pandas UDF, and we are using apply in the group by, and the difference in 3.0 is that we are using typing information from Python 3.6 or 3.7, and we're using apply in Pandas. That's the only difference. I mean, I think it's cleaner, so it's good. It's easier to use for other kinds of UDFs. For this one, which is a kind of a group map is the weirdest one, so it doesn't improve much. And how it's, sorry. So this is a diagram of how the group and aggregation would work before a row and after a row. So you have a driver, which Python and everything, and executors, which are also going to execute Python. You have a data set that is going to be shuffled according to the grouping. So when you group something, the data needs to be in the same machine. So if you are grouping by ID and you are going to sum or do some computation, you need to have all the same IDs in the same places. Okay, this is distributed. And then, well, each worker is going to do something with the UDF and everything. And then the data is sent back to the driver. This is the pre-arrow approach. Where you would have needed to do something like this, which is kind of horrible, because you couldn't use UDFs. So you group, send to Pandas, and then group by in Pandas. So instead of having this here, where everything is being distributed and computed in each machine, in this case, we would have that everything needs to be computed in the driver at the end, which means that the driver needs to have memory for all of the groups if the executors have any of memory for all the groups, which usually is not the case. So this is the kind of operation that before was impossible, basically, and now it's possible, because in this case, you wouldn't have enough memory in the driver. And the summarization I always give, I mean, it's like the too long didn't read, it's that use arrow. I mean, it's just changing a flag. The flag by default, it's false. I think in 3.0, I think it should default to true, but I'm not 100% sure. If it's not, just set it to true, because if you are using something to Pandas, this is cheap. And try to rewrite your UDFs into Pandas UDFs. The difference in speed, it can be 100 times or more in a speed up. So there's no reason not to do it. You can find the slides in my GitHub, and there are a lot of references in the end. Links to the Spark documentation, very good books. And I would suggest that you become a contributor to Spark. I mean, there are a lot of issues, like a lot. I mean, probably open issues, there are like 10,000, maybe not, but 1,000 or 2,000. And there are a lot of pull requests that you can go and have a look at what people are doing, maybe review something, which is always work that gets delayed. And it helps you understand how Spark works, how open source works, and it will make you a better developer and also a better open source citizen. And now it's time for questions.
Thank you very much, Ruben. We have some questions. The first one, it came along during the presentation. What is doing the PySpark community to improve performance of PySpark, knowing that passing by Py4G can impact harder the processing? So I'm not sure, because I think all the effort has been moved to using Arrow to avoid the serialization cost. So I'm not sure if there's much more work being done to optimize, because right now, if you compare the runtimes of the same computation done in Scala with DataFrame API and doing more or less the same, like a multiply by 2 or something more or less simple or some group by operation, in the end, what you do in Python and what you do in Scala is equivalent. So if you never use a UDF, for instance, if you are only using a standard operations like group by ID and count or something like that in PySpark or in Scala, the difference in execution time would be almost zero. And by using the arrow optimization, Pandas UDFs, and all of the things I have mentioned, basically the execution time, I think it can be, I mean, the worst case scenarios go like it's 1.2 wars, which is like, it can be still improved, but there's not much room for improvement. I mean, for instance, one room for improvement that is still available is that the
Pandas group map that I have shown as an example, that's not super optimized for memory, and it's open. But there's not much more I remember being worked on. I think there's some work in having inter-process communication from memory directly in the Arrow data format. So basically, you can share the memory between the JVM and the PySpark side. But I think this is still kind of very far. And that would be a pretty big speed up, but I think I don't remember what's being done in that area.
Okay. And this question came when you were talking about Arrow. Is there one Python worker by partition or one by executor core?
That's a good question. I haven't never checked. I think there's always a Python executor by, a Python worker by executor. So each executor is going to raise a 1-1 worker but it could be one per partition.
Okay.
I think it's one per partition.
Okay, and we have, I think, time for 2 more questions. Why using 2 pandas to get all data of the driver and not using partition by and then map partition to leave the data on the worker?
I guess that's for... So it depends on what you are doing and at which point. I mean, and in the end, this was an example to show that the speed up is significant. There are eventually times that you need the data in the driver. So this is where using 2 pandas would make sense. You would use the map partitions one, for instance, in this situation where you would like to map the partitions. The thing with map partitions is that this is an RDD only operation. So you can't get Spark to optimize it for you with DataFrames API. So you lose a lot of power. So, I mean, I always try to, I think I haven't used map partitions in a couple of years. I mean, I try to avoid it because if you use it and you start adding code after these map partitions, you lose all the optimization that the Spark is going to give you, which it's kind of a lose. But of course, in this example, you could have done many other things like using map partitions in, where was it? In this one. But I didn't want to go there because I wanted to show how it had a speed up. Also, this is easier than using map partitions in the end.
Okay, and one last question. Is Scala UDF call from Python still faster than using Pandas and Arrow?
In general, yes. So if you have a UDF defined in Scala and you import it in PySpark, the Scala version should be a bit faster because even if the serialization cost is way lower with Arrow, it's still something it's being change sides and change operations. But it depends a bit on the data format because since Pandas is going to be columnar and Spark is not always operating columnarly, I don't know if that's a word. Some operations may be faster if you do them in Pandas UDF and Arrow instead of using UDF. So it depends a bit on the case. I mean, I wouldn't change code I have as a Scala UDF into a Pandas UDF if you have it already defined. But instead of moving a Python UDF to a Scala UDF, I would move it to a Pandas UDF first, because I think that would give the easiest optimization because the code stays Python, so you don't need to learn Scala to do that.
Thank you very much, Ruben. You can find the link for our satisfaction survey in the comments. Don't forget to fill out. I'll see you in some minutes for the next talk. You can find the link in the comments. Our next talk will be about data architecture, Glue, and EMR. See you later.